So happy Monday, digital world. This is DataViz Bob here. We're very excited because we're preparing for an exciting data visualization exam. And we have some questions, but before I get to the questions, today happens to be my dad's birthday, so happy birthday, Dad. I don't know if my dad actually watches these, but if he does, then happy birthday, Dad. Back in the US. So this video is dedicated to two students. The first one is Ala Al-Sharari. That's the anglicized pronunciation of the Saudi name. And Ala asked, what is an advantage of the first ray traversal approach, regular sampling? As far as I understood, it is the most computationally expensive, which makes it a disadvantage. But what could it be an advantage? What could be an advantage? And the second question is, what is a disadvantage of the third approach? So there are more questions, but I'll just start off with those two. So just a quick review. We talked about approaches to ray traversal in the context of volume visualization with a special focus on direct volume rendering. So when we cast a ray into the volume, that's what this is trying to depict. The ray samples the data. Now in this case, the data is stored on a regular grid, right? And the data is stored at the corners of the grid cells. And when we shoot a ray into that volume data, in this case it's projected onto 2D, there are different ways we can sample the data. And they have advantages and disadvantages. Right, so in the first case, the regular sampling, now these blue dots are samples of the volume data as a ray is being cast through from front to back. Now I've tried to draw it well. So this is characterized by an equal distance between each sample along the ray. And that's what this means. The distance between one sample point and the next sample point is the same. So this distance is supposed to be the same between all the sample points. Now, that is the advantage of that is that it's very accurate. Right, so I'll check there. The disadvantage is that it's not so fast. So maybe I'll just put an X to the marker is all dried out. Let's try this one. Now, why is it accurate but not so fast? So it's accurate because as it's traversing the volume, it's using more samples in the volume to do its interpolation. Now, in the two-dimensional context, right? This is, I'm keeping track of the number of samples used in the interpolation process and the number of interpolations necessary. So this is actually supposed to be a 3D ray passing through a cube, right? This is the entry point. That's the next sample, and that's another sample. And this is the 2D case, right? So in order to accurately sample the data here, for example, I need to interpolate 3 times. So imagine my data samples are stored at the corners. What are the 3 interpolations? So I have to interpolate once along X, again along X, and then along Y to get my sample point. And in 2 dimensions, that's 3 interpolations. This is the number of interpolations. So that's 3 interpolations in 2 dimensions for every data sample point along there. And the number of samples that it uses, the data samples, are 4. So it uses 1, 2, 3, 4 data samples to interpolate and derive all of the samples along the ray. In the 3D case, I try to draw that. It's a little bit trickier in the 3D case to draw. We have an entry point. We have a data sample that happens to be on the plane. But for any general point inside the cell, we need 7 interpolations, actually. We need 1 along this X, 2 along this X, 3. We can interpolate along X 4 times, and then we can interpolate along Y twice to get these, and then we can interpolate again along Z, the final interpolation, in order to get the data, the interpolated data at the center of the cube or anywhere inside the cube. And I hope that shows up on the video. Actually, that's going to be a little bit tricky. I hope that shows up. Now that's regular sampling. So regular sampling is accurate because it uses the highest number of samples, but it's not so fast because the number of interpolations is high. It's the highest for the 3 strategies. So every interpolation slows down the computation. Now the other one is another one. These are just 3. There are more than 3, by the way, but we only talk about 3 in the class. Another one's called nearest neighbor interpolation, or nearest neighbor ray traversal. So we cast a ray into the volume, and as soon as we enter a cell, we just take the value at the center of the cell. It doesn't matter what that is, and we keep going. As soon as we enter another cell, we just take the value at the center, and we keep going, right? Every time we intersect a cell, we just take the value at the center, right? This is also called nearest neighbor interpolation or scan conversion, right? Now this requires actually no interpolation. So no interpolations at 2D and no interpolations at 3D, right? So there's the 3D case. We're just taking the value. Now how do we get the value at the center? There are 2 ways. We could pre-interpolate, so interpolate before we run the algorithm, so we have data values stored at the center. Or we can just shift that grid over so that these data values are at the centers instead of the corners of the grid. So we just shift the whole grid up and over by 1/2 of a unit, and then we have all of the data stored at the centers. So Is that fast? Yes, this one is fast, right? Because it requires 0 interpolations, and interpolations are costly, right? They require computation. Is it accurate? No, it's not accurate. Why is that? It's because of this case here. The distance between samples is not uniform. So look, there's a big distance between these two data samples, right, all of a sudden, right, and the distance between these ones. And look, we have a sort of a jagged sampling of the volume as it traverses the volume as this ray passes through. So we had a little hiccup, technical difficulty with the recording. I'm going to pick up where it got interrupted. So just to repeat, the nearest neighbor is the fastest and the least accurate. Now the third approach are the voxel intersections approach. Now that attempts to be a compromise between speed and accuracy. So the sampling takes place always when the ray intersects the voxel boundaries or edges. In 2D, these are edges. In 3D, these are planes, right? Notice how there are two samples very close together, and these are not so close together. Now, the advantage of that is there are fewer interpolations necessary to compute these data samples. In the 2D case, there's only one interpolation necessary, and it's always along the edge, right? Here, it could be along this edge, assuming that the intersection is along here. Here we have one interpolation along this edge, one interpolation along this edge, and so on. This is a schematic of the 3D case, where we need 3 interpolations every time. So we would interpolate, for example, once along Y, again along Y, and then a third time along X, right? And then we have our 3 interpolations that we need every time the ray intersects the face of a cell, right? It could also be along X, the first, so we sample for, or along Z in this diagram. So we interpolate once along the Z there, once along Z here, and then once along Y in the Y direction, assuming that X points in this direction, Y points in this direction, and Z points outward from the camera or into the camera, right? So this is attempting to be fast because it requires fewer interpolations in 2D and 3D, and it's kind of accurate too. That's an approximation symbol. The distance between samples is never it's never equal. Well, it's not equal, but you don't get these big gaps, these big distances that happen in the nearest neighbor interpolation, right? And you're actually using more samples from the data to get your fast approximation, right? You're either using 2 samples in the 2D case or 4 samples each time, data samples each time in the 3D case. So back to the original questions, what's an advantage of the first ray traversal approach? It's the most accurate, the first ray traversal approach, right? And as far as I understood, it is the most computationally expensive. That's correct, which makes it a disadvantage. That's correct. So it's the slowest but most accurate. What is the disadvantage of the third approach, the voxel intersections? Well, one could say a disadvantage is accuracy, right? Because you don't have the even spacing between samples, like you do the guaranteed even spaces between samples along the ray. So you could say that that's a disadvantage. It's trying to be a compromise between these two approaches, right? Now the third question from Ala is, what do you exactly mean by grid types used in visualization, and what is its topology? What do you mean by topology? Now, Ala's looking at the previous exams, and there's a question about grid types. You don't have to worry about grid types for this exam, so that content has been moved out this semester. We used to have a few slides describing grid types. This happens to be a grid type. It's a Cartesian or uniform grid, right? The samples are evenly spaced. And there are other grid types, but you don't have to worry about this topic, this grid types topic this semester. That was a topic we used to teach, but it's been subsumed, it's been taken out and replaced with other material that's a little bit more fun, let's say. Now there's a question here about topology. So when we talked about grid types, we used to talk about geometry and topology, a grid geometry and a grid topology. But you may remember this word topology can be used in lots of different contexts. And we do talk about topology in its meaning in the lecture on graphs. So topology means a set of entities and the connections between them. So we have a look at the lecture on graphs, the introduction lecture on graphs, and you'll notice we'll talk about topology, and I'll put a link in the description of this video as a refresher on that. I also have, I'm going to feed two birds with one scone. We're not going to kill any birds. We're going to feed two birds with one scone. Thank you, Harold Thimbleby, for reminding me to use that expression. I have another question from Casey Denner, which happens to overlap. Thanks for the revision session. It was very helpful. I've looked over a few more past papers and have some more questions. What are the three different grid types used in visualization? Identify, describe, topology, and geometry, which was basically the same question that Ala had. So no, we didn't cover grid types, so there is not going to be an exam question on grid types this year. And those grid types have nothing, well, those grid types, you don't have to worry about those grid types. Casey did ask another question. Are these types of sampling, such as regular scan conversion or voxel intersections, or am I on the wrong track? You don't have to worry about it. I could make another video, though, that describes the different grid types and how those rays would traverse the different grid types. It starts to get more complicated. This is the simplest grid type, so that volume data is usually sampled on this simple grid to make it easier to sample, to traverse using rays. And she asks, comparison of glyphs in tree maps, when do you use them and for what data? So remember, glyphs we use in the context of n-dimensional or high-dimensional data, right? Because glyphs can encode a pretty arbitrary number of dimensions. We talked about the special case study of rugby glyphs. We talked about star glyphs. We talked about different kinds of vector glyphs and their variants. So glyphs are usually used to visualize abstract multivariate or n-dimensional data. And tree maps are usually used to visualize hierarchical abstract data. So one's n-dimensional, one's hierarchical. And then it starts to get really interesting if you think about trying to visualize multivariate data with tree maps. It is possible. It's not easy, but it's possible. For example, the size of every rectangle in a tree map represents one variable. Well, you could use color to represent a second variable, and you could use maybe something like opacity to represent a third variable, and so on. So there are ways to visualize multivariate data with tree maps. That would be, by the way, that would be hierarchical multivariate data in the case of trying to use tree maps. She also asked about the disadvantage of voxel intersection ray traversal. So this one, and one could say that disadvantage is it's not as accurate as the uniform sampling, right? You also get this case sometimes with the voxel intersections where samples are very close together, and that's extra computation. Doesn't necessarily happen very often, but you could argue it's a disadvantage. Okay, I hope that was a helpful video. Yeah, let me know if there are any more questions, and good luck on the amazing test.